Hey guys, welcome back. This is the last one that we'll be doing before spring break, so I hope you guys enjoy this. If you are watching this from home, if you want to go out and get some M&Ms, you can get a fun size bag of M&Ms or just like the standard size M&Ms from gas station or whatever. You can participate along with us. I think you're going to enjoy it. So I went to the M&M's website, Mars and Mars, and this is the distribution of the color of the M&Ms. So surprisingly, 20% are orange. The most common is blue, which is 24%, I guess, because people like blue. And then the least common was 13% of all of the M&Ms. They're saying that this is basically the distribution of the color of M&Ms for the entire population. So of all the M&Ms that they produce, they're claiming that 20% of them are orange. Now we will learn how to do chi-square testing at the end of the year, which will be pretty cool, and we can actually see how unusual any one of our samples are. For maybe you had a lot of red or a lot more green or something like that. We'll actually do this experiment again, just looking at small samples with chi-square data at the end of the year, which would be kind of fun. But for today, we're only looking at proportions of orange M&Ms. So let's go ahead and get started. So open up your bag of M&Ms, but before devouring them, record the number of orange candies that you have and the number of candies that are in the bag. So the first bag that I opened, because I actually ate 3 of them before the bags even made it to class. It was the weekend. It looked good. So the first one that I opened, it had 15 candies in it altogether, 15 M&Ms, and of those, there were only 3 that were orange. Well, I can't really say only because 3 out of 15, I believe, is 20%. So I actually had exactly the amount that we would expect out of 15. We would expect on average to have 20% of those, which would be 3 orange M&Ms. What was your sample proportion? So open up yours. If you have a very large bag, you might have more than 100 M&Ms in there. I probably wouldn't do it if you buy like a massive big like 2-pound or a pound bag of M&Ms. Maybe just scoop out a handful of those randomly selected and then sort those out. That'd be totally fine. So what was your sample proportion? Basically just put it in the calculator and divide it. I had 3 out of 15. So I had a sample proportion of 20%, which is exactly what I would have expected. So what was your sample proportion? Was it higher than 20%? Was it less than 20%? Do you think that you had enough evidence to suggest that yours was, that there's not actually 20%? So does yours seem out of the ordinary? Well, we can actually calculate a p-value, but the problem is we can't use our z-scores because our samples are not going to be large enough unless you have a really large bag of M&Ms. So we actually want to use the binomial distribution. So let me do my other example. So the second bag of M&Ms that I had was had 14 of them in there. The probability of success is 0.2 for the binomial. And so this is the distribution of all the possible number of orange M&Ms I would expect. So on average, 2.8 is our expected value. And I actually had 2 orange out of these 14. So to find a p-value, because it's less than 20%, I actually want to do 2 or less. So the CDF going to the left, so that or less, which is a p-value of 44.8%, which is really close to the average of about 50%. So that would be a very common observation and would not be statistically significant. So in other words, the p-value would be calculated if the true proportion was actually 20% orange M&Ms, then the probability of observing a sample statistic like this or worse, which is 2 or less out of 14, a small bag of 14, would be a probability of 0.448. Now, whatever alpha I select, the sloppiest alpha we would ever use, even for candy, would be 10%. And since this proportion is larger, the p-value is larger than 10%, we would not have had enough evidence. This would not have been statistically significant. So while I've got you here, if you want to go ahead and navigate to the link for the Google Sheet, this is all the data that we've done today. So I had to wait to make the video because I had to get the data from my students in order to show you guys. So go ahead and go down to yours. So Murphy here. All right, so the first bag of M&Ms that I opened had 3 out of 15. So for trial 1, I'm going to go down to my name and put in 3 out of 15. Okay, and what's cool is as I do that, it will be updating the cumulative relative frequencies of the percent of orange that we had as we opened up our bags of candy. Now Excel does this in order from the top to the bottom for each trial, so you're not necessarily going to be able to find yours very easily, but it'll be in there. And so then if you have more bags of candy, you can actually go ahead and put it in for the second trial. So the second one I opened had 2 out of 14. And then the third one I opened also had 2 out of 14 that I devoured. So some cool stuff I can go ahead and show you here. So what we have here's the cumulative totals. So I took the sum. Yeah, I guess you can actually read the formula if you want. But I took the sum of the cumulative total of that we've tested all together. So it's like if we started with Anna and she had 13 out of her small bag, and then 13 more from Ashley. So altogether, this is the total number of M&Ms that we've tested. So after our first trial, towards the bottom here, you'll see we had 33 out of 171. From our second trial, we had that number, and then at the very end, this is the total number that we had altogether, which is 95 out of 521. Now, this data obviously will change after you guys do the experiment, which would be pretty cool, but you can use this data for, and I'll be using this data for the video up to this point. So the next thing that I want to point out is the cumulative frequencies. So this is going to be the number of orange that we had at that point in time, which from the first one, 1 out of 13, that's that percentage. That proportion did not change because we had the same 1 out of 13 from Ashley. Then it went up. Well, actually, I can graph that out, and you can see those totals going around there. Now, towards the end, we had less than 0.2 pretty much the entire time, except, well, no, we never had more than 20%. So we were always on the low end, which is interesting because when I did this last year, we were always on the high end. Okay, then the last thing is the p-value. So if we're doing an alpha level, which we'll talk about that later, but we're going to select an alpha level of 10%. Then the p-values, we'd have to have anything that was in the top 5% or the bottom 5% in order to be able to reject the null. Now, at no point did we have that, but let me just kind of mess with the data so you can see it real quick. So if she had 0 out of 13, that would have put her p-value at this point and this point here below 5%, the bottom 5%, which at that point would have been able to be statistically significant enough for us to be able to reject the null hypothesis. But she actually had 1 instead of 13, so that didn't actually happen. And then you see the conditional formatting. So if you, just kind of spoilers, if you look through here with all of our p-values, none of them were in the top 5% or the bottom 5%. So we did not have enough evidence, at least so far without your data, in order to be able to reject the null. And we'll also have the rest of this be filled in on Thursday after my B students do the rest of the experiment. So kind of cool, really fun to see all of you guys put all this data in here. Thank you, Google Sheets, for this live document. That's a lot of fun. So you can do the binomial distribution, calculate your p-value. Let me show you how to do that in the calculator real quick. Same thing, we're going to do distributions. So second, distributions. Towards the bottom, it will be the binomial CDF. I'm going to do the 14. So out of 14, probability of success 20%. We're going to go up to 2. So from the left, 0 to 2, and then hit paste. Now, if you're doing it from the right because you had more than expected, then you just do 1 minus 1 less than the number that you found. Of course, that would work out just fine. So that's how I got my p-value here. So did that seem out of ordinary? Not at all, because I had a very high p-value. Write an appropriate hypothesis and choose an alpha level. So our null hypothesis is that there's no difference or no change from what we expected, which would be 20%. So that would be that the proportion of orange M&Ms actually is 20%, like claimed by Mars and Mars. Our alternative is going to be one-sided or two-sided. Well, it's not just the one-sided upper or lower. We would be concerned if it was anything but 20%. So if it's less than 20% or more than 20%, either way, we'd be upset, or that's what we're trying to prove. Is it different than the 20% that was claimed? So that would be a two-sided test, which is just simply that it's not equal to 20%. The true proportion is not 20%, whatever we think it is. We'll go from there. Our alpha level, remember, we default to 5% when we're dealing with candy, when it's literally not that important, like what we're dealing with right now. We can do the sloppiest alpha of about 10%, which is what we'll do. If it's life or death, we might do 1%. In rare circumstances, we might even do 0.1% or 0.01% alpha level when we have to have a very high significance level or burden of proof, such as like we were talking about, like the death penalty or something like that. All right, so what alpha level we select is also going to be the same as the type 1 error. So the probability that we call it Mars and Mars and tell them we think they're full of crap, like I did last year, maybe, and we're actually wrong, and it was just random sampling variation. So whatever we select, if we do a sloppy alpha of 10%, like if we had 10% on one side, if it was a one-sided upper test, there's a 10% chance it actually is 20%. We just so happen to have a 10% a 1 out of 10 of our samples would be in the top 10%, right? So since we're doing a two-sided test and our alpha level was 10%, there's actually going to be 5% on each tail, because collectively that would be a total alpha level of 10%. So that's kind of what we're looking for, top 5 percentile or the bottom 5 percentile, which you can see we were graphing those out here. So you see the p-values, anything that's in the bottom or the top 5% would be considered unusual enough for us, or significant enough for us to be able to reject the null hypothesis in favor of the alternative, saying that it's not actually 20%. All right, so let's go through our conditions. So random sample, is this a representative sample of the population parameters? So the population interest is all the M&Ms that have been made. They're claiming that 20% of all the M&Ms are orange, so that they're claiming our P, or our P naught, if I wanted to fill that in. I guess I can, there's nothing stopping me. So P naught is equal to 0.2. So that's what we're claiming. Our sample proportion is going to be whatever we get from our M&Ms. Now the M&Ms that we are sampling frame is all the bags of M&Ms that I brought to school, or the bags of M&Ms that you guys bought. Hopefully our sampling frame, which is all the ones that possibly could be chosen, are representative sample themselves of the overall sample proportion. Maybe they all came from the same batch. Maybe that batch was overrepresenting the orange or underrepresenting. I don't know, but kind of interesting. And then the actual sample itself is going to be the ones that we actually were selected, the bags that we opened from the bags that I brought to school or that you guys purchased. So we hope that the sample is representative, and I think it should be. And then we just have our sample proportions as we go. Now 10% condition. Since we're sampling without replacement, whenever we eat an M&M, it's no longer there and we can't select it again. Technically, when we're sampling without replacement, it's no longer independent because the probabilities are changing, just like in cards. If you have 2 aces, the probability another ace is going to be drawn is no longer the original 1 out of 13. It's changing. But as long as we're sampling less than 5% or 10% of the overall population, which would be 5.2 cards, so 5 cards, it's okay. Even though the probabilities are going to change, it's not going to change our conclusions, or it's not going to change the probabilities enough to change the outcome of our conclusions. So that's, are we sampling less than 10% of all M&Ms? Certainly, I did not buy more than 10% of all the M&Ms that are in the world. So we're good to go. All right, success, failure, conditions. So this is to make sure that our model is not cut off by a hard left bound of 0 or the hard right bound of n. So we need to expect at least 10 successes and failures. Unless you're using a really large bag of M&Ms, you probably didn't have, we're not expecting at least 10 orange candies and 10 that were not orange candies. I mean, that part you would. But so what is the smallest one, the smallest sample size that we could do in order to use our normal models, expecting that? Well, if you divide n times p is equal to 10. So if we divide by 0.2, 10 divided by 0.2 on both sides, we would get 50. So basically, let me go ahead and show that in the calculator. So 10 divided by 0.2, the smallest sample size we could have in order to use z-scores and our bell curves and one proportion z-test is a sample size of 50. So we would need to have several small bags of M&Ms, at least 50, or just pull all of ours together like we did in our Google Sheet. Then we're totally fine. So let's pull our data together by inputting into Google Sheet, which hopefully you've already done that. And let's put them into the calculator. So I'm going to pull up the Google Sheet real quick, and I'm going to go to Stat Edit, and my lists are already populated. I've already got stuff in there, so let me quit out of that. And I'm going to clear all of my lists. So I'm going to go to second +sign memory in the 4th options, clear all lists, and hit enter. And now whenever I go to Stat Edit, they're going to be empty. Okay, so for list 1, I'm going to put all of the orange totals. Just go in order here, and we're going to do all 3 of the trials. This might take a while, especially for my Thursday kids. So if you want to do just the first trial, that's totally fine. I don't blame you, but I'm going to do all of them because I can, and mainly because I can pause the video and I don't mind. So I'm going to start this off, and then I'll show you what it's going to end up doing. So like 1 1 3 3 3 5 3 1 4 2 3 4, yeah, 10 key, pretty awesome. And then for the totals, 13 13. I was a cashier at Aldi, so I've got a good 10 key. But anyway, I'm going to do the other ones, and then I'll be back in just a second, okay? All right, so now that we have got all 36 of our bags of candy, or 36 of our individual trials put in there, the next thing we want to do is we want to find the cumulative number of not heads, the cumulative number of orange M&Ms that we've done. So that's the running total from list 1. So to do that, you actually can do it from this menu here. If we arrow up to list 3, then we can actually define it here. But I'm going to quit out to show you a different way of doing it. So that follows the instructions. So what I'm going to do is find the cumulative sum, which is going to be found in second stat, the list menu, go over to operations, and then the cumulative sum is the 6th option. So I'm going to do the cumulative sum of list 1 and then store that, STO, as list 3. All right. Now I'm going to do the same thing for list 2, which is going to be our total number of M&Ms that we have sorted, and I'm going to do the cumulative sum of list 2 and sort that as and store it as list 4. So now if I go back into stat edit, list 3 is going to be the number of running total of orange M&Ms. So from the first one we had 1, and then after that we had 2 because there's one more, and then 3 from Diana, which would put us up at 5. And then it would be 5 out of 43 because there were 43 M&Ms total that we had sorted. All right, so if I go towards the bottom, that's where we're going to get our final statistic of, should be 95. Looks like I might have a typo in here out of 251. Okay, so I have a typo somewhere in the one column. I'm going to see if I can find it. I'll be right back. All right, I found my typo. This one actually should have been a 4. So I will fix that real quick. And then if I need to rerun those, so that was from list 1. So it's kind of good to show you that anyway. Let me quit out of that. So I'm going to rerun the cumulative sum of list 1, store as list 3, hit enter, and then if I go to stat, edit towards the bottom, now it's fixed. So it's 95 out of the total there. All right, so this data, I mean, it's all there, but this is pretty tough and difficult to actually interpret. So the best thing we can do is make a picture, right? So we'll go to second y equals a stat plot, just turn one of them on. We're going to do a line graph instead of a scatter plot because we actually want to see the trends as it connects between the two, even though it's, you can pretty well figure it out as a scatter plot, but we want to see the trend lines or the trends connecting it as time goes on or as our sample increases as we open up more and more bags. So our X list is going to be the actual total number of M&Ms that we've sorted at that point, which is list 4. And then our Y list is going to be, I need to do something else. So we need to find the cumulative relative frequency of the orange M&Ms as we go. So that's actually going to be list 3, the total number of cumulative sum of our orange M&Ms divided by the list 4, which is going to be our total number of M&Ms that we've done so far, and then we need to store that as list 5, and that's going to be our frequencies. So if I go to stat edit, this is the frequency of orange M&Ms that we have as we go. Now you can actually see that exact same thing right here in the Excel sheet. So our final proportion was the 18.23, same thing we got here. All right, so go back to stat plot, and I'm going to graph that as our y-axis because that's the actual response variable that we're interested in, seeing how those proportions change as we open up more and more bags of M&Ms and our sample increased. So I'm going to plot this. I like the plus signs because they're precise and you can see them, and then do zoom 9, and that's going to graph it out. Okay, cool. So this is our cumulative relative frequency of the orange M&Ms as our sample size grows. Now what we might want to compare this to, if you want to go to y equals, I'm going to go down to the orange one just because I can, because it makes sense, to 0.2 and then hit graph. So this is what the empirical probability should be, right? It should be 20%. And so as we started out, of course, our samples are very small, and so they're very volatile. And then as we increase our sample size, the law of large numbers tells us that the empirical probability should approach the true probability of 20% or whatever it actually is as our sample size go to infinity. Now, our sample size, even though 521 is not a small sample size, it's still not. It could get worse. It still could get better, closer to 20%, less, further away from 20%, just like we had here. Any short run behavior is still possible. So the law of averages is not the same thing as the law of large numbers. The law of averages is a false interpretation of just the short run behavior of the law of averages, which says as our sample size go to infinity, or as our trials and our simulation go to infinity. So it could get better, could get worse. I don't know. We'll see what happens after Thursday and after you guys put in more data. But so far at this point, we haven't had enough evidence to be able to reject the claim yet. So, okay, did part F, gotcha. Did our sample proportion converge or diverge from the 20%? which was our empirical probability. So it looks like it's converging to it, but at points it actually went away, but it looks like eventually it will converge to it, but we don't actually know. Again, the law of large numbers, it says as it goes to infinity, so we can't actually tell. So yeah, we can't tell. Look at the last row of list 4 and list 5. That's going to be our final sum of orange candies, which is 95 out of 200 or 521. This will give us our final stats in order to test the claim of is the null hypothesis actually equal to the proportion equal to 20% and to write a confidence interval. So our total orange frequency that we had was we had 95 orange M&Ms altogether. You can see that from our spreadsheet out of a total of 521 M&Ms that we sorted collectively. So thank you guys for helping with that. So what was our sample proportion? I guess I'll just pull that up real quick. So our sample proportion, our final sample proportion was 18.23. And of course that was the 95 out of 200 and, or 590 and 521. Whew, dyslexia. All right, there's supposed to be 20% orange candies. Does our data contradict this claim? So let's run a test here. So I'm clear all that stuff out. I'm going to go to stat, arrow over to test, one proportion z-test, which is the 5th option. Our hypothesized proportion is 20%. We had 95 out of 521. We're doing a two-tailed test. We just want to know if it's different than the 20%, not just greater or lower, one tail upper, one tail lower test, then hit calculate. All right, so our z-score is -1 essentially, which is 1 standard deviation below the mean, which is not considered unusual. Our p-value is 31 percentile, so we were in the bottom 31 percentile, which is not unusual. And the worst alpha, the sloppiest alpha we would select, even with candy, is 10%. And so we're looking for a p-value that's less than 10%. And we didn't get that, right? So our p-value was more common than our significance level, so we failed to gather enough evidence to be able to reject the claim that they were actually telling the truth. So at least at this point, maybe this will change later after we get more data, but we don't have enough evidence to suggest that they're lying to us. All right, so you can do that. Next thing we might want to do is create a confidence interval. So that's pretty much what we did here. Instead of having 10% on one side, we actually did 5% on both sides, which should be about here. And our sample proportion, which was just basically right at 1 standard deviation below the mean, was not within the bottom 5%. So we were not able to reject it. So what was our conclusion? Did we reject the null, or sorry, were we able to reject the null hypothesis, or did we fail to reject the null hypothesis? We failed to reject the null hypothesis in favor of the alternative. Okay, so fail to reject. Carefully explain what the p-value means in context. The p-value, the p part of the p-value is the probability. So it's a probability value. It is a probability, and it's specifically a conditional probability based on the assumption that the null hypothesis is true. So if there actually was 20% orange M&Ms, the probability of getting observing a statistic like we did, which basically this area right here, or worse, is going to be that probability, which was the 34%. Okay, so move that back there. And we failed to reject the null hypothesis because it was not, our p-value was higher than our alpha level. So basically, there's two things that could happen. If the true proportion is 20%, it'd be centered there. If it's not, then it's centered at the true proportion, which is possibly somewhere else. There's the difference between our hypothesized proportion and the sample proportion that we actually got, which is the last one we did is our best guess, best estimate. The standard deviation for the sampling distribution model is where we calculate our p-values based on. That's because it's fixed and we know what our hypothesized value is. So that's the math, and that's basically the sampling distribution model. Now, based on if that was actually not true, then our best estimate is that the true amount of orange M&Ms is about 18%, 18.3%. And so if we correctly rejected it, so if we put our alpha level at this 5% here, then this would basically be a type 1 error, which would be 10%, because there's actually a 5% on the other side too, but we're only doing, it was lower than that, so I'm only having to show one side. All right, so if we correctly rejected it, then that would be the power of the test, which looks like with the sample size we have without decreasing the margin of error, and the effect size, a difference of only about 2%, which is what we observed at least so far, it looks like the probability of us being able to detect that difference is only about 20%. And we actually failed to detect it because we were on this side of it. Okay, and then that would be a type 2 error if we accidentally rejected it when we shouldn't have, or type 1 error if we rejected and we shouldn't have, and a type 2 error if we failed to detect the difference because there either wasn't a large enough effect size or our samples was not large enough. But we should be able to nearly double the sample size by the time we're done on Thursday, which would be kind of cool. All right, so we've already gathered more data. We've already put most of this in the calculator. The only other thing we want to do is this margin of error, which is absolutely fascinating. So if you've actually got it on yours there. So let me show you how to graph the margin of error. So we're going to do the lower margin of error. So I'm going to do 0.2 minus 1.65 because we're going to do a 90% confidence interval times the square root, which is second x squared. And I'm going to do alpha x to do it as a fraction so you can see exactly what I'm doing. Our hypothesized P naught is 0.2 and 0.8 is Q naught. Our sample size was 521. Oops. Okay. So what I want to do instead of 521, I want the margin of error to change, and this is actually like the key here, to change as the sample size increases. So I'm going to put this as our x variable, which makes this actually a function instead of just a fixed value. Constant, right? So as we increase our sample size and our scatter plot goes further to the right, if I go ahead and click graph, as we increase the sample size, so cool, you will see our margin of error decreasing. Now we're only looking at the small part of the margin of error. If it was positive, we would look at the positive part if we were over that, but we never went over 0.2, so we don't have to worry about that. So at any point that we cross this margin of error here, at least with a 10% alpha level, then we would have been able to have a statistically significant observation to be able to reject null. So let me zoom in here if I can. How close we were to having statistically significant observation in the bottom 5 percentile. This is honestly just a warning. We know that our samples are more volatile. That's why I have a larger margin of error at the beginning, but we could have, if we were not honest statisticians, we could have stopped gathering data or just ignored the other data as it actually converged and said, ooh, look at this point, it was past that, and then just ignored all the other M&Ms we opened, pretend like we never did that, and then stick with the conclusion that we were wanting to do and call it Mars and Mars and call them out on their BS. So basically it's just a big warning that there's a danger in cherry picking the data or fine tuning the alpha level. I could select a sloppier alpha level in order to be able to cross that. So if I show you that here, so let's do 1.4 instead. I'm not sure what confidence interval that actually is associated with, but we could find that. And at this point, it actually would have crossed here at this point, and maybe again over here if it was even worse. So we could have fine-tuned our alpha level to give us the results that we wanted to be able to reject the null hypothesis. So it's very important not to cherry pick data or to fine-tune an alpha level for some predetermined conclusion that we were interested in. So don't do that. We can run another confidence interval with 95% confidence if we wanted to. Let me actually go ahead and show you that real quick as well. So if I go to stat, go to test, I believe it's towards the bottom, alpha, or 1 proportion z interval. That's going to be our last statistics, 95% confidence interval, and then hit calculate. So the way we would interpret the confidence interval is we're 95% confident the true proportion of orange M&Ms based on our sample is between these two values here. Now notice since 20% is still contained in our interval, then that means it was not statistically significant, right? We believe it's at least 95% confident that it's possible that 20% is actually the true proportion because it was within our confidence interval. If we wanted to do the same thing but do a 90% confidence interval, go to alpha, then I'll just change this to 0.9 and then hit calculate. Now we're 90% confident the true proportion is between these two. Even with that sloppy of an alpha level of 10% alpha, we still think that there's a chance that the true proportion is still 20%. So we would have failed to reject the null hypothesis in this case as well. So that leads us to our last statement for the day. A quote from Mark Twain about the danger of cherry picking data and the bad reputation that stats has. Oftentimes people are politically motivated whenever they come up with some experiment, and they will do a lot of really bad things. There's one thing even worse that you could do. I guess I'll even talk to you guys about it because I can. What if I took all the data that I gathered and I sorted it from least to greatest? So if I took this, all right, so if I took all of my data here, and I could do the same thing over here as well. If I had it all in one column, it would work even better. Okay, so I'm going to do sort the range by column A. Now at that point, because I started out with the worst case scenarios, Oh, this is so deceptive. Then at this point here, because I started out with only the small ones and ignored the ones that were the bigger ones, that would have given me p-values that were below the 5%. So just a fair warning. It's hard to trust people these days, right? And there's just so much agenda going on. But there's a lot of ways that stats can go wrong. So be very careful with how you gather the data, all the different types of bias that can come in with the sampling. That's probably the most common. But even when we're analyzing the data like we did here, there's some really shady practices that can be done. Don't do those. Don't cherry pick your data and throwing out stuff that you don't like just because you don't like it. Clearly don't sort the data. That was wicked rude. And then also don't fine tune your alpha level to get some predetermined conclusion that you were looking for in the first place. Look at the data honestly, unbiasedly, let the data lead you to conclusions. And then if you're reading a study and stats, a lot of people don't know how to interpret stats, and so take their interpretation with a grain of salt. Even if, regardless of what source it's coming from, actually look at the data and the studies themselves to make sure that they're interpreting p-values the way they're supposed to. Margin of errors, if they're not giving you margin of errors, that's pretty shady. Or confidence levels, stuff like that. There's a lot of things that people will just throw out because they don't understand it. So do better than that. Be a good consumer who actually understands what's going on here. And probably the biggest issue that we see altogether is correlation, of course, is not equal causation unless we have a carefully designed experiment. We just because there's a trend between the two things, there can be all kinds of lurking variables or confounding that's going on in the experiment that doesn't allow us to make those conclusions. We wish we could, because that would be cool, but there also can be other things going on. That's where we look at multivariate analysis, where we're not just looking at one thing versus another, but of all the things that are going on, which one has the highest correlation. And then from there, we would do the carefully designed experiment to see if we assign music education or no music education, whether or not that's actually what's going on. Okay, so be wise. And I have been on this for way too long, so I will see you guys later. It was a really fun lab, but I'll see you guys later, and I hope you guys enjoyed it as well. I'm looking forward to seeing the rest of the data on Thursday as we fill in the rest of this.